This ring true to everybody so far? You got F in your head? You got P in your head? Okay. Let's fix the error. Let's dial some I in here. All righty. What value should we start at with I? See if everybody's learned. There should be a sign beside it that says, trick question, don't answer. We're actually going to start at 0.005. Okay, last time it was 0.5. Now why is this 0.005? In general, a good starting point for I is P divided by 100. Whatever got P pretty happy, that got you that stability, I is that divided by 100 will get you a good starting point, where it'll have an effect and it won't go crazy. Okay, so P divided by 100 is a good starting point for I. So remember that teaching when we have the D discussion. All right, so we're going to dial 0.005 into I. And we'll screen line. And this thing is running wide open. Huh. Anybody know why? You have to be quiet. You have experience. Why is this running full speed? Okay. We spent quite a bit of time screwing around trying to get P sorted out. Remember that integrator bucket that fills up with water if there's air? We've had a lot of air for about the last half an hour. How full do you think that bucket is? Let's look and see. That bucket, remember we added that value, is the integrator accumulator, is right here. It's this green value. It is currently 690,000 some odd number, and it is counting down. So the integrator is saying, hey, you are going too fast. Take some water out of that bucket. I've got my valve open backwards because I'm going too fast and I am taking water out of that bucket. But that bucket was really, really full, and so the water level's coming down. We're now down to 400,000. Still a pretty big bucket, and it's pulling water out of that bucket as fast as it can, but that bucket was really full. Meanwhile, that full bucket times my p-value equals way more than 1,000, and this thing's running wide open. When does it actually slow down? Well, we're down to 300,000. When does this actually slow down?
About another 4 minutes.
Okay. That's our team timekeeper, and he's saying you're not going to actually be able to let this run to the end point. If we hung around here long enough, it would eventually empty out the bucket, and you would hear this, and now it'd be going exactly the right speed. The integrator was, as he said, way wound up. That bucket was really full. The rate at which I can take water out of that is limited, and it takes a long, long time to get that bucket empty. Because right now, well, we actually might wait this out. We are down to 100,000. So this whole time, we've been taking water out of the bucket.
And this whole time, what's going on? You're having a discussion with other people. The thing's still running. I don't know what's going on. And all of a sudden,
once again, you're over asking the mentor, what's going on? And the mentor's thinking, I don't know, but I'm not going to say that out loud because I don't look like an idiot. But you must have done something wrong. And so, you're all wandering around, and suddenly it runs the right speed. And the student asked the mentor, well, what happened? Oh, I waved my hand over it. You're good to go. So that is an extreme example of integrator wind-up. That bucket, that integrator had been cranking the whole time. Even though we didn't have any value in there, there was no output. There was air, and it was integrating the air. That's going on all the time. Now, the moment we put in an I, it said, okay, that bucket times my I value, I suddenly have an output. Before, that multiplier was 0, and I got nothing. Now, a really small number, 0.005, times one of those white tanks of oil on the side of the road is a really big number, and you just watched what happened. It took that long for it to get that bled down. Remember before me talking about this thing called I-zone, and we really wish we'd have that later on? That later on would be right now. So, if we look at our value, first of all, let's see how good of a job we did getting it to run the right speed. We actually turned I on to try to integrate the air and drive this to the right speed. We wanted 300, we have 300, the error is 0. Seems pretty effective. And there was much rejoicing. This is when a cheer goes up.
Yay!
Yeah, okay. So now we have a PI loop with feed forward enabled, and we can make this thing run the right speed. Let's see how crazy it is. And the response isn't awful.
And we're watching the green line, right?
Yeah, watch the green line. And once again, the orange line is just that air amplified. But I let go of it, it slows down, it overshoots a little bit, but I settle pretty quickly. I don't see excessive ringing. So this is not awful, that's not too bad. For winging it on a couple of values, this is pretty close, okay? But then there's this bucket problem. What do we do about that? This is where I-zone comes in. I-zone is a value you set in the Talon. And this has a lot of different names in the commercial world, but it's to deal with integrator windup. This is an integrator, accumulator, bucket of water, clamp. And in the Talon, the particular way this thing operates is when you have checked the box for this, it opens a really, really, really big hole in the bottom of the bucket. And all the water instantly disappears, and any amount of water you're putting in disappears. So when I-zone is enabled, the water flows out of the integrator bucket instantly and keeps flowing out instantly. Okay, I can empty my bucket that way, but great, how do I make this thing work? You actually enter a value, and let's say I entered a value of 25 here. The I-zone value is watching the error, and when my error gets below a certain level, it seals the hole up in the bottom of the bucket. So what goes on, if I have a big error, big hole in the bottom of the bucket, effectively the integrator's turned off. I'm counting on F and P to get me roughly to the right speed. And if you remember, when we just had F and P in there, it would get me at 300, I think I was, what, 290. So I'm 10 counts off. If I set my I-zone to 25, it will keep that bucket empty until my error is within 25 of my target. Then it seals up the bucket and the integrator starts working. So what would have happened if I had turned I-zone on at a value of 25 before it finally bled the bucket down? It would say, hey, you are running 700 speed. That's way more than 25 past your 300 target. You're outside of the I-zone. Empty the bucket. And so the bucket is instantly empty. You're now back to simply P and F doing the work. But as soon as that motor is within 25 RPM of the target, that bucket gets sealed up and you now start integrating the air. And that system will keep that bucket empty until you are close to your target. Then it enables that, and now that bucket fills to the right amount and you don't deal with this overfilled bucket. So that's what I-zone does. In general, where do you set I-zone at? You set up F, you set up P on whatever real system you have, and you look at if it's velocity, you look at whatever range you're going to run it in. Let's say in this case, you're going to run it from 200 to 500. I go check, okay, at 200, how far off am I? I'm off, 20. At 300, how far off am I? Well, 18. At 500, how far off am I? I'm off 10. Okay? I'm going to set I-zone to 25. Because you have to have that zone big enough that P and F can drive you inside of that window, or I will never turn on. So it's got to be big enough that F and P can get you in the window, and once it gets there, I will take over and finish it up. Now, the reason you don't make I zone really big to guarantee I just always get it, the bigger I zone is, the sooner the integrator starts working, and the integrator, even when you are on the way to the right answer, can get wound up a little bit too far, and it'll make things overshoot. So you might have I at about the value you want, and there's still some overshoot in it. As you clamp down I zone, you are waiting to the last possible moment to turn that on, and that bucket starts as close to empty as possible and settles right in. If you start it way early, it will start integrating the air, and that bucket will be too full by the time you get to your goal, and it will have to overshoot and come back, and it might even oscillate a little bit. That's what makes you want to have I zone tight. If it gets too tight, and you can't ever get inside of the window, I never turns on, it won't run the right speed. We actually had a problem on the Stronghold robot shooting those balls where the firing velocity of that was pretty critical. And there was a particular sequence of events where you could end up with that robot out on the floor, all spun up, and those wheels was like 2 ticks away from being inside of I zone, and it was sitting there stable, running the wrong speed. It's like forever, what's going on? This thing worked 10 minutes ago. And indeed, I zone was a little bit too tight. So that's what I zone is. That's how you fix the integrator. Okay? All right.
Question.
Yes.
Is there a way to detect from the software side? I guess you could do it. Never mind.
So you can always watch the integrator accumulator and see how full it is. That's why we plot it. I have it as a purple line. You'd see it scream across the screen. Obviously, none of my scaling went to 400,000. I think I have it mapped on the green one. But you can always see the value, and that will quickly tell you what's going on. Now, while that was counting down, if I had entered 25, you'd suddenly see that thing snap to 0 because it just pulled the bottom of the bucket out. And as soon as I got within 25, you'd see that thing now start to count. So I'm actually going to go enter in I zone to 25 right now to get that out of the way. All right. So let's see what we've got here. Okay. Not incredibly beautiful, but not awful. That's one way to get a sense of what's going on. The other way to get a sense of what's going on is you just do a step change. Oh, okay. Wrong place. So there is speed of 200. And I'm going to do a step change to 500. Big step changes, in essence, lets you see what the response is, and it's much more controlled than me grabbing it with my fingers. For gross checking, it's easy to just load something with your fingers if you can. If you have a gearbox at a gazillion Newton meters of torque turning at 1 RPM, you're not going to affect it. You've got to do something like this. All right, and so I'm now going to step to 500, and then we're going to stop this. Okay, so I have got a iZone enabled PI controller with F, and when we look at where we're at here, I was at 200, I told it to go to 500, it took off there, I overshot a little bit, but it didn't ring, it settled right in, and when I look at my error, yep, I fixed it, I overshot a little bit, I came back, but I settled pretty quickly, and I needed just a little bit of air. The integrator is going to drive this to 0 to get everybody happy. So that's reasonably stable. Now, in a perfect world, I might want to get rid of some of that overshoot. So I wonder if D could help me out here a little bit. All right, so let's go back to 300. Whoop, wrong screen. Okay. All right. Where should I start with D? You've been coached.
What would Jerry say? I've seen the bracelet.
Ah. All right. So if to do I, you basically take P and divide it by 100. Okay, starting point for D, you might think, okay, take P and divide it by 100. Interesting guess, you'd only be wrong by a factor of 1,000. Turns out D, a good starting point, is about 10x of P. We could also spend 6 hours going through the math of Y, just trust me, that's a good starting point. Once you know what P is and your system's kind of stable, that's going to give you a good starting point for I and for D. And it all comes back to getting P right, helps you sort out what's my encoder, what's my system, that gets you within the range, and then those two multipliers, and that's all in my cheat sheet notes at the end. 10x for D is a decent starting place. And so right now we have got P at 0.5, I believe. Yep. So we're going to put D at 5. Okay. And we're going to start doing this more officially so we can see what's going on. Okay, and we're going to do another 200 to 500 step change and see what that looks like. Okay. As it turns out, believe it or not, that is actually a little bit better. I still overshoot, but if I look at my error didn't blow out the bottom quite as far. So, not as much effect as I'd like, but it actually helps. So, when a little seemed to be good, what do you do next? More. What could go wrong? Almost like you know something's eventually going to go wrong here, like this thing was rigged. All right, let's turn this back on. Put this back at 200. Go back over here to... All right, and so what we're going to do, normally I would show you 10, then 20. We're going to save some time. We're going to go straight to 30. Okay, let's get ready here. Here is 200 to 500. Okay. Now, for those that have been in control loop programmers for a number of years, you start to get really excited now because this is starting to look very pretty. I did my step change, all pretty controlled, and boy, it's not perfect, but my overshoot is appreciably decreased, and my error, which gives me a much bigger view of this, boy, remember it used to go clear the heck down here? Now just a little bit, and boy, we settle in, and this is not bad. And that is approaching almost a magical step change where my motor's going a speed, it steps to the new speed, there's no overshoot, there's no undershoot, everything is just as I would like it. So, I say, you know, I'm a greedy guy. That's almost perfect. Let's go for perfect. Let's crank a bunch more D in it. Not teaser, something bad's going to happen soon. All right, so we'll go back to 200 here. And so we're going to do 2 and D is 3. We did 30. I could double it to 60, but we want to go for dramatic effect, so I think we'll go to 120. All right. Now the good news is, I entered that in and nothing crazy happened, but then again, D is only multiplied by my rate of error change. How much is my system changing right now? Not. So D doesn't do a lot when it's sitting still. So let's go back and change the speed. We're at 200. We're going to go to 500. Let's see if we can capture this. Well, isn't that interesting? All right, and here's the thing about D. D is very noise sensitive. D is taking my rate of change of my error and multiplying it by a value. The steeper my rate of change, the bigger effect D has. If I have noise on my error signal, let's say this is running at 300, but it's bouncing up in minus 50 because my encoder is junk and I have very low resolution encoders and I just got noise in it. All that noise gets multiplied by D. Noise in your system gets in the way of using D in a hurry because D doesn't care if your error is really changing or if your error is just noisy. Any change of that error signal is going to get multiplied by D and get into your output. And as you crank D up, things get interesting. This was my voltage that used to look nice and pretty, and now it oscillates, but what's up with all this craziness? Well, if we were to really zoom in on the error that's way up here and even here, there's little bits of noise in here, and D is so high that that little bit of noise, that is a very rapid change, gives you a big D effect. And as you crank D up, you will start to see all kinds of crazy things grow in your graph, and it's because D is amplifying any rate of change, and what matters is the rate. Even if it's a small change, that is momentarily a high rate of change, and you will get a nasty spike on there. And if we kept going, fascinating things would happen, and all of them bad. So you can crank D up until things start to get goofy and noisy, and actually, you'll notice now it doesn't overshoot at all. As a matter of fact, it completely spazzes out. I think I can, I think I can't, I don't know what I'm doing, and eventually it gets to the right answer. Now, what we could do, we could go back and I don't know, probably about 35 would be the ideal answer. We're going to go back and set it at 30 because that's a pretty good stable answer. You could tweak around a little bit with it, but that showed you how much you got in trouble. And look at the current here. So this whole control loop is just nutsoid trying to get to the right answer. Now also notice, I didn't go from 30 to 31. I went from 30 to 120. You got to keep in mind the scaling here to really get a sense of, am I seeing the effect? Am I really as far as I need to be? So let's put this back at 30. All right, so remember this train wreck here. And back at 30, let's see what we get. And something that looks a lot better. And see how this now makes some sense? I still have a little bit of noise in here, and that's D, but it's okay. That's small enough, it's okay. This is all under control. I settle pretty quickly. I look at my error signal, that's all okay. The purple here, this is that bucket. When I first said go from 200 to 500, my error is instantly 300. 300 is bigger than 25. So it says empty the bucket. Bucket's empty. And it is only within, when that gets within 25 of 500 that it says, okay, start doing something with the bucket. And you see this thing now chasing my error, and eventually to drive this to perfect, this thing has to be at a value that's off the screen. It actually has to be at a minus 1900 to get things to go to 0. But you actually see that bucket activating and taking off to the right answer. So that is D. And what you now have here, when you look at the green line, I have pretty good speed control. Let's turn this back on. And indeed, you get quite a bit of current trying to slow this thing down. And if I did this, The instantaneous event here, that is P and F trying to, or really it's just P trying to fix this. I is too slow to instantly fix those dipsy doodles, but, okay, watch the 200. I am going to put some load on this. And what speed was I at there? Yeah, and so the integrator on a slow nature is chasing that back up. And if I varied my load slowly, the integrator would keep this thing at 200 RPM until my fingers caught on fire, which they pretty much did. So keep in mind the integrator can't fix it instantly, but the integrator will eventually get it fixed. Now, I could keep cranking my integrator value up, say, I need it fixed faster. Well, but then it starts to oscillate, and you have crazy things happen. So this is all a game of how aggressive can I be with P, I, and D to get to the right answer as fast as possible with acceptable or maybe even no overshoot and not have it oscillate. And you disrupt the system, you know, by doing these step changes. I'm here on the bench going from 200 to 500 and I watch that step change. And if I put that same tuning back in there and I came and did this slowly, it would look nowhere near as bad as that 200 to 500 jump when I had I too high or D too high. That step change is the best way to see where you're at. If you get it to where your step change looked like our 200 to 5 with the D at 30 and this stuff, and it looks that good on the screen, out on the playing field, it's going to be outstanding because you are typically not doing those biggest step changes. So this is by far the best way to do that. So that is P, I, and D. So we're going to take a break here in a second. Yes?
Can you correlate the mass and the performance of that grid to how it impacts the motor on, like you say, a robot in the way it performs? Because ultimately, that's where this really shows up.
Yeah. Ultimately, at the end of the day, you want your velocity or your position to do what you want it to do when you want it to do it. And it's configuring all of this as optimally as you can to get that thing to do what you want it to do as fast as possible, as stable as possible. Keeping in mind, to your point, there is no magic wand. If I need to accelerate that robot from 0 to 17 feet per second in 6 inches, not going to happen, and there's no amount of tuning in the world going to fix that, because all 4 motors wide open blowing the breaker, you can't get there that fast. You are limited by your fundamental physical plan. The control loop can't fix it outside of the fundamentals of your battery and your motor and your mechanism. It can only control it inside of there. Okay? Yes?
Just to add to it, when it's tuned right, all of a sudden your driver is now able to control the robot a whole lot better.
There are folks that have speculated when they watch Jack, and Jack's not here today, drive that robot on the floor, they're like, that's the best driver in the world. Don't know how he's doing it, never seen a robot do that before, blah, blah, blah. Now I would tell you, Jack has spent a lot of time driving that robot. The folks doing the tuning have also spent a lot of time figuring out how do we make that robot do things that match up with Jack, and it's a system together. So yes, you can solve things that are hard for a human to do by fixing them here. But as Mark, the videographer in the back of the room, who's also one of our senior mentors, will point out, humans pretty freaking smart. Don't try and fix a problem in the robot that a human can fix in a nanosecond, because you're just going to go crazy. And it's splitting up. What does the driver need to do? What does the robot need to do? But yes. Now, when we operate that robot in auton mode, it is full velocity control on all the drives, and there's all kinds of precision going on. You might think, when we're in tele, that he's driving that drive in velocity mode, where when he says to go a certain speed, it does. We don't. That thing is driven in open loop voltage mode when he's in tele. We got a heck of a human right there with eyes on the field, and there's nothing more stable than voltage mode. Never going to oscillate, never going to do anything. And in voltage mode, if you lose an encoder, you don't care. If you lose all 4 encoders, you don't care. It is the most robust way to run that thing in tele. We just run it in voltage. Now, you got to have your 4 wheels in a swerve kind of matched or the thing drifts, but we run it in voltage in tele for that exact reason. Okay? All right, so you got PI and D. We're going to take a break. This makes some sense to folks. You're now through the trickiest part of this. And now, tomorrow you'll try to remember all this and go, oh my God, my head's spinning. There's the cheat sheet. It's about starting out slow. Make sure your motor and your encoder and your hardware is wired right, doing what it's supposed to do. If it's not, your chance of succeeding with the PID loop is 0. Your chance of going crazy is 100%. Make sure it's right, then sneak up on it. Figure out F if you need it. Figure out P, figure out I. Don't use it if you don't need it. If 10 was an acceptable error, don't use I. Only use what you need to, because the more of this stuff you use, the trickier it gets. Honestly, this looked a little easier than it really is, because I've done this for a long time, and this was all scripted. Yes?
Drive system.
Yep. Yes, when we are in, now obviously in tele, we just run voltage mode, so there's no F.
Right, so it's programming.
In programming, yes, when we're in drive mode, all 4 wheels are programmed exactly the same as far as their closed loop control. I talked a little bit about filters that are in the Talon in the velocity loop. And you can think of these filters, it is math that goes right here. It is taking the raw information coming out of the encoder, doing some stuff to it, and stuffing it in there. And those filters were enabled in the middle of last season, and they can be unbelievably useful when A, you really, really need them. You shouldn't use them unless you really need them, and B, you really, really understand what's going on. It is very easy to get yourself in trouble here, which is why in the beginning, Cross the Road just hard-coded them. It was over-filtered to guarantee nobody had a problem, but you actually gave up a little bit of performance in the Talon. And what you can think of this as, when we were doing the walk the line exercise here, there was a lot of stuff going on to make sure the encoder, figuring out how far off the line he was, that was really accurate, and all the noise had been stripped out of it. And that really came in the form of these guys have a confab and say, what did you see? I don't know, what did you see? Well, let's add it all together, and okay, here's the value. You need to go left or right. Well, all that takes time. And time, as we saw, is your enemy when it comes to getting feedback. Also, though, if your feedback is noisy, you need to go left, maybe, or maybe right, or maybe left, I don't know for sure. If your feedback is noisy, that's bad too. So it's a balance. And what you can now do in the Talon is actually adjust that. And there are 2 values. And this is only used when you're in velocity mode. When you're in position mode, this is not used. Position mode is straight encoder position data right into the map. And so here's how it works. This was actually an Excel spreadsheet we built to basically synthesize the effect of these filters on actual real data. So in this graph, this is RPM, and this is the RPM of a particular shaft. And that is the instantaneous real RPM. You then look at the encoder, which is also tied to that. It's actually going at real speed, but that encoder has some kick rate that's coming out of it, those rising edges on the quadrature encoder. And if you look at the tick rate, that's what this scale is. So the red is the motor shaft and the orange is the tick rate, or basically the rotational speed of the encoder in terms of ticks. On this graph, the only reason that the orange line and the red line are offset is because they're on two different scales, and I offsetted them so that the red and the orange didn't sit on top of each other. So really the orange is what is the raw encoder physically doing? It is running at that rate. If you look at how a Talon is programmed up with its inherent filter, and its filter has two elements. If you are going to measure speed, and all I can see are these ticks that are going by, and say, okay, there's a tick. What time was it? Okay, I'm hanging out for a while. Here's a tick. What time was it? Okay, I went from here to there in this amount of time. I now know the speed. I don't know what the speed was in the middle, but the average speed between those two endpoints is something, and that's my speed. And in the Talon, default is 100 milliseconds. It looks at the position of your encoder. 100 milliseconds later, it looks at the position of the encoder and says, okay, do some math. This is the speed on average that thing must have been running during that 100 millisecond window. So when you start thinking about that, you say, well, okay, but gee, yeah, that was a 100 millisecond window. A lot can happen in 100 milliseconds. You know, those guys confabbing, trying to figure out what speed he's going, a lot has happened, and they're yet to offer that answer up to the control loop. And so, where am I at? 100 milliseconds later, where am I at? How fast am I going? And so at the end of that, you can output that. Now, as it turns out, the Talon does that every millisecond. So the way to think about that is, let's say at time mark 100 milliseconds. A bad example. At time mark 10 milliseconds, I'm going to figure out how fast I'm going. I'm going to wait until 110 milliseconds, and I'm going to look at where the encoder is at. I know how far it moved. I know how much time went by. I can figure out the average speed. I also marked down where the encoder was at 11 milliseconds, and at 111 milliseconds, I'm going to do that same event. So every millisecond, I get an update. But that update is based on what happened during the last 100 milliseconds. So, okay, I'm getting updated every millisecond. That sounds plenty fast. But my data is kind of 50 milliseconds old, because I have a 100 millisecond window. I'm measuring how far that moved. And depending on what you're doing, that can be a little bit of a problem. The other thing they hit in there is there's noise in the system. I might do that math and it says I'm going 500. And I do the math a millisecond later and I'm going 530. And I do the math a millisecond later and I'm going 490. Well, wait a minute, it didn't change speed that fast. It's all about noise in the system. That it's about zero error where I had 1 plus, it's where the edges fall and the quadrature signal and everything. There could be noise in that. Their second layer of filter is saying, okay, I'm measuring 100 millisecond windows. I'm doing a new one every millisecond, so these things are just one after another. And then how many of those 1 millisecond updates am I going to average together before I finally offer up, here's how fast I'm going. And default in the Talon, it is 64. So when you look at how a default Talon measures velocity, they're saying, okay, mark 1, where was the encoder at? 100 milliseconds later, where was the encoder at? Look at that delta. It moved this far in 100 milliseconds. It must be going this fast. And at that moment, at that 100 millisecond mark, that's the speed. A millisecond later, it offers up a new speed that is based on a 100 millisecond window offset by 1 millisecond. Then it takes the latest 64 values, averages those together, and calls that the speed. The good news is you get nice, stable RPM out values. They're not all noisy and they're nice and smooth. The bad news is that all happened like 6 years ago. And when you're trying to do a control loop, delays in your encoder cause a problem. Now, they were actually pretty smart about how they did this. This can get complicated. They put values in there that pretty much guarantee everything works. Where you pay a price is on a high-performance system. You may actually have more delay in that encoder stuff than you really need, especially if you have a high tick rate encoder. If during that 100 milliseconds, I only get 5 pulses, okay, I have 5. And if on the next 100 millisecond window, I caught the edge of the next pulse, I got 6. Well, I didn't go from 500 to 600 RPM. I have a resolution problem because my window is too small given my encoder rate. If I had a killer encoder, so I don't know, 4,000 counts per rev, I can actually tighten those windows up because I have enough counts that my 1+ error won't get me in trouble. And so, at the middle of last year, they opened the door where you can now program the window as well as how many it averages together before it finally offers up the number. And here's the effect of that. And this was all based on this shooter. I'm running at a speed, it doesn't slow down instantly, but I puke a ball into it. And my speed is going to slow down some amount from that. And my motor shaft is going to do the red. I'm going to assume I'm going to throttle up and get it shoved back. My encoder is simply going to do exactly what the red thing did. They're on the same shaft, just scaled a little bit differently. This is over encoder ticks. Once I go through the 100 millisecond window and look at what comes out the other end of that, what does that look like instantaneously versus what's going on in the real world? That is this green line. The orange is what really happened. The green line is what comes out of phase 1 of that filter. It's way behind, and we lost a lot of the amplitude. And that's all because we're filtering. Now, if you end up having a very low encoder count tick rate, you need this stuff or it won't work. And that's Cross the Road had to do this to deal with the worst case scenario. Turns out in the best case scenario, it's way overkill and you've given up loop tuning because they detuned this to make it work for everybody. Phase 2, which is how many of these samples I average together, that takes you to the blue line. So when you look at a standard Talon, if I'm running, say, 12,000 RPM, and I have a step change, and I want to recover that, say, in 100 milliseconds, I have a step change. My feedback, when I think about my air amplifier, my feedback doesn't even peak until 100 milliseconds later. My Talon doesn't even have visibility until 100 milliseconds later that that thing is even at this speed. Oh, and by the way, it says, you're actually not going nearly as slow as you actually really were. And this all happens with filtering. Now, if they didn't do this, really bad things would have happened to a lot of folks. But if you're going to push this thing to the limit, this stuff gets in your way. You can program both of these now. And for example, same event over here, I have got the yellow or the orange is what's really happening, and I change that sample period from 100 milliseconds to 25 milliseconds, and I change my how many samples am I going to average from 64 to 8. The blue line, which is actually what the air amplifier sees, is no longer that, it's now that blue line. And you can see up here, and that's how close it gets. So that thing becomes a whole bunch closer to real time, and that lets you do a lot. When the ball hit that thing, you need it to be up to speed in 100 milliseconds. You don't need to be just finding out it slowed down. The moment the ball hits that thing, we wanted 50 amps going into that motor to get it back up, and you had to do a bunch of stuff like this to get that thing to recover that quick. So, yes?
So when you went to the 25 milliseconds and the 8 samples, you were changing your sampling rate too then?
Well, in essence, sampling rate didn't change. We were tightening up the window. How long do I wait to actually determine my velocity?
Okay.
So now you have to look out for an N+1 problem. You got to have enough counts in there that your resolution
Right.
is still okay. And then your filtering, you still got to take enough noise out of it so you don't have noise going into your thing. And
But you quartered your period and you got only an 8 sample.
yeah, 'cause what's going on, I've gotten rid of the delay. What has happened is here, the delay is knocking the amplitude of this off because in essence, when you average all this together, that's what you get. And this was all modeled on the exact math that really goes on in the Talon. So we could put in numbers and see this is what the Talon's really doing. So if you have a 100 millisecond measurement window, what comes out of that, this run through that, you get the green line, run through that filter, you get the blue. If you simply change that, you're right, this only has a quarter of the counts in it. You still do the math. You know I changed my period, so I got to multiply that by 4. So I still get back, but I'm losing resolution. Now, if you have a high enough tick rate encoder, maybe I don't care. That my N+1 problem doesn't get me yet. If I have a really slow tick rate encoder, you might not be able to do this.
In the case of the shooter, Doug, the shooter was moving fast enough to get enough counts, so he didn't have an N+1 problem.
Yeah, but I'm looking at the period going down by a 1/4. Why didn't the samples only go down to, why did the samples go to 8 instead of 16?
Oh, no.
Oh,
Those are two different values.
Okay.
Now, those are two different parameters. The first parameter says how long is the period I use to measure velocity.
Right.
I do that every millisecond. I update. The second one is how many of those 1 millisecond answers do I average together before I finally spit my answer out.
Okay.
Two independent values that I could have left the second one at 64. As it turns out, when we looked at what we could do, I could dial the first one down to 25 and I'm still okay in my resolution. I could dial my second one down to 8 and I'm still okay in my noise. And at the end of the day, I get the blue line over there versus the blue line here. And now when a ball touches that wheel, that Talon rails that motor instantly, and you're pumping energy into that thing right away. Now, I offer this up so you guys know it's there. Unless you are dialing something right up to the limit, don't go here. You can get in trouble. You already see the noise over here? Well, you're starting to have a resolution problem. See how choppy that is? That is because we don't have as many counts as we used to. Things are a lot more unstable. I start feeding that into my PID loop, I start to get noise I didn't used to have, and I'm trying to ping that loop now and get it upset, and it's because my signal coming in is messed up. So this is here if you want to really dial something up to a Formula One race car level. You need a bunch of experience before you go here, or you're just going to explode the system, and everything's going to go crazy, and you're not going to know why. Just know that's here, and that's the kind of impact that you can have. But when you see in there, it's called window, and what's the other thing they call it? It's window and bin or count or something. They don't actually use the word period in samples, but there's two places to tune that. So know that that's there. You need to be pretty desperate before you mess with that. And if you do, feel free to call us and we'll give you some advice. Okay. So very quickly, I'm going to show you the effect of that. And Jeff, on the pulse, do I need a space before the time or just comma and the number? Okay. One of the features in TCT that developed from the need to tune this, we'll do that again, is to say, hey, TCT, I want you to do this speed change for this period of time and then stop. I can do 0 and go to some value and stop, or I can be at a value, go to a different value and come back. And what that's for is all this impulse tuning. I need a step change, and what this really was derived from If you're trying to do velocity tuning on a robot on the floor, you need to do a step change. And you do a big step change, and that robot is now at about a zillion miles an hour headed across the floor. You have about 3 seconds for something to not get in your way before that robot smashes into something someplace and really bad things happen. So we did this so that when we're tuning a robot on the floor, I say go this speed for 3 seconds and turn off. I don't care if I died in the meantime. You shut off. You do not need any further input from me. Go that far and stop. And it's very, very useful to guarantee we don't run the robot into stuff. So this is where we ended. And that is a 200 to 500 tick rate change and back. So you see pretty similar response, accelerating and decelerating. All I'm going to do is go tighten up that filter and make that filter a little faster. Now it's going to introduce a little more noise, and let's see what happens. All right, so that's where we were. Okay. On my error before, I had a lot of interesting stuff going on. And this actually cleaned things up a little bit. And I simply did that by changing the velocity tuning. Now, this is helpful when you have got a system that's very nimble. We have a pulley with nothing on it. Or I have something where I need instantaneous response. Like a shooting wheel, that a ball's going to hit it, and the moment I see that thing start to slow down, I want to firewall the Talon and get a lot of energy back into that. Unless you hit those limits, I probably would not go here, because you can get yourself in trouble. Because if you take this filter down too far, things will start to happen, it'll start to oscillate, you won't know why, and you won't know if it's the filter, the PID, and you'll get to start all over and build it back and figure out what's going on. Another thing that you can do, let's make sure I get those values correct. Okay. Another thing you can do is we talked about that voltage ramp rate, where I am simply going to limit how fast the output to the motor can change. It's another subtle thing you can do to try to dampen things out. In this particular case, I'm going to slow that down just a little bit. Okay, and so now we'll turn this loose again. And go 400. All right. What that was, with all this tuning we've done, and all the different tricks, it was running 400 forward. I said, I want you to now go 400 in reverse. And then I want you to turn back around and go 400 forward. Just as brutal as we can make it, we're going to hammer on this thing and see if it's stable and does a good job. And here's my velocity. Very nice turn here, very little overshoot. It's not like the arrow's going crazy. That's great. It got to that speed. That's about all the faster we can change it. You get down here, you're good. I head back up, I'm nice and stable. That's actually a pretty sweet closed loop graph. It's very controlled. I could go in and do 200 to 300 to 500, whatever, and it does whatever I tell it to do. The accuracy is there, and it's a nice, clean transition. I could probably do things to speed that transition up if I had a need for it, but that's pretty stable and pretty clean, and that's really what you're after. So that's the full set of tricks that you can use to tune a velocity loop. questions before we screw up our physical plan. Okay? All right.